Hi all. In last lecture we gave an introduction to cycloaddition reaction and typically Diels-Alder reaction. We discussed about the mechanism of Diels-Alder reaction. Okay, next one, types of dienes and dienophiles. Types of dienes and dienophiles. We have to familiarize some typical dienes and dienophiles. Okay, first one, dienes. Some common dienes. Diene containing two pi bond. Okay, dienes are acyclic dienes are there, cyclic dienes are there, exodienes are there, aromatic dienes are there. For example, our acyclic dienes, what are the common acyclic dienes? For example, the typical 1,3-butadiene is a typical acyclic diene. Another example, substituted 1,3-butadiene. This is also an acyclic diene. Then next one, next example, this is also an acyclic diene. Another one, this is another example for acyclic diene. All these are dienes in Diels-Alder reaction. So these are acyclic dienes. Then cyclic dienes. Cyclic dienes. Cyclic dienes. For example, an example for a cyclic diene. This is an example for a cyclic diene. Another example, substituted cyclopentadiene. An example for a cyclic diene. Another example, this is also an example for cyclic diene. One peculiarity is all these are in cissoid conformation. Two pi bonds on same side. Two pi bonds on same side. Two pi bonds on same side. Here also two pi bonds on same side. So our diene must be in cissoid conformation. Our diene must be in cissoid conformation. Acyclic diene, cyclic diene. Then third one, exodiene. 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 Have you heard about exocyclic double bond? Exocyclic double bond. This is an example for an exodiene. Here a double bond, here a double bond. An exodiene. Another example for an exodiene. Exodiene. This is also an example for an exodiene. So acyclic diene, cyclic diene, exodiene. Then next one, aromatic diene. Aromatic diene. For example, furan. Furan. Furan is a typical example for an aromatic diene which shows Diels-Alder reaction. Which shows Diels-Alder reaction. So furan is a typical example of an aromatic diene which shows Diels-Alder reaction. Actually, when aromaticity is very high, the aromaticity of the ring is very high, then Diels-Alder reaction is very slow. Okay, when aromaticity is very high, aromaticity is very high, slow Diels-Alder reaction. Slow Diels-Alder reaction. Okay, when aromaticity is very high, slow Diels-Alder reaction. For example, compare these three aromatic system. First one, thiophene. Next one, pyrrole. Next one, furan. Comparing thiophene Then pyrrole and furan. Which one is most aromatic? Comparing thiophene, pyrrole and furan, which one is most aromatic? Sulfur having the least electronegativity, so it is the most aromatic, then pyrrole, then furan. Okay, so thiophene is the most aromatic. We will discuss the aromaticity of heterocyclic compounds in the heterocyclic section. We have a section, reactions and aromaticity of heterocyclic compounds. In that section, I will discuss about the aromaticity of these heterocyclic compounds. Okay, so comparing thiophene, pyrrole and furan, sulfur is the least electronegative, so it is having the highest aromaticity. Highest aromaticity means thiophene shows slow Diels-Alder reaction. Thiophene shows slow Diels-Alder reaction, but furan is the least aromatic. So furan is a typical example of an aromatic compound which shows Diels-Alder reaction. Furan is a typical diene which shows Diels-Alder reaction. Another example is your anthracene. Anthracene. The middle ring of anthracene act as the diene. Okay, the middle ring of the anthracene act as the diene. Very, very important. Give a star mark. So we have acyclic dienes, we have cyclic dienes, then we have aromatic dienes, then exodiene. In aromatic diene, which are the typical examples of aromatic diene? First one furan, and this is anthracene. Then some special dienes. Examples of some special diene. For example, this is an example for a special diene. Here also these two double bond act as the pi bond. These two are the dienes. Okay, this pi bond and this pi bond, a special diene. Then another example. This one also act as a diene. Then another example. This is also an example for a diene. Then another example. This is also an example for a diene. Here these two double bond act as the diene. Okay, so we discussed 5 classes of dienes. First one acyclic diene, then some cyclic dienes, then some exodienes, then some aromatic dienes. Furan show Diels-Alder reaction, but thiophene show slow Diels-Alder reaction because thiophene is highly aromatic. Then some special dienes also. Okay, clear? Then types of dienophiles. First one, acyclic dienophiles. For example, this is an example for a dienophile. Here a pi bond is there. Then another example for an acyclic dienophile, cyanide. Then another example, CO2R. All these are examples of acyclic diene. Then acyclic dienophile. Then cyclic dienophiles. For example, this is an example for a cyclic dienophile. Another one, all these are examples of cyclic dienophiles. Then the most important This is called malic anhydride. Malic anhydride. Very, very, very important. Give a star mark. Malic anhydride. Malic anhydride. Then another example, quinone. 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 This is also an example for a cyclic diene. Diene containing a single pi bond. Acyclic, cyanide, ester. Then cyclic dienes. Here malic anhydride and quinone is very, very, very important. Okay. Then some special dienophiles. Some special dienophiles. Okay. Some special dienophiles. For example, selenium oxide. Selenium oxide. Typical example is selenium oxide, sulfur oxide, selenium oxide, then sulfur oxide, then nitrogen oxide, CH3 plus, then PPH3 plus. All these are examples for some special dienes. Okay, special dienes. This selenium oxide, sulfur oxide, nitrogen oxide we will discuss in pyrolytic syn elimination. In this lecture we will discuss about pyrolytic syn elimination. There we have to discuss about the selenium oxide, sulfur oxide, nitrogen oxide, etc. Okay, so that is special diene. Special diene. Then fourth one, special dienophile. Then dienophile in alkyne form. Dienophile in alkyne form. For example, our benzene is a typical example for a dienophile in alkyne form. Benzene is very, very important. Benzene is very, very important. Then acetylene or ethine is a typical example for a dienophile. Then another important one is ketene. This is a carbon. Okay, this is a carbon. This is called a C double bond O. This is called ketene. Okay, C double bond O. In ketene, this carbon double bond acts as the dienophile. In ketene, the carbon double bond acts as the dienophile. Okay, so we discussed about dienophiles. First one, acyclic dienophiles, then cyclic dienophiles. After that, some special dienophiles like sulfur oxide, selenium oxide, nitrogen oxide, PPH3 plus, and also diene in alkyne forms such as benzene and ethine. Then also ketene also acts as a dienophile. In ketene, the carbon double bond, C double bond C acts as the dienophile, not C double bond O. Okay, that's about types of dienes and dienophiles. Next, reactivity of dienes. Very, very important. Many times questions are asked based on this concept in B part questions mostly. Okay, reactivity of dienes. The two factors which affect the reactivity of diene. First one, diene must be in schizoid conformation. Our diene must be in schizoid conformation. Second factor, reactivity increases when diene contains an electron donating group. Reactivity increases when diene contains an electron donating group like OR, OH, NH2, etc. CH3, etc. Okay, so these are the two factors affecting the reactivity of diene. First one, diene must be in cissoid conformation. This is the cissoid conformation. The two double bond on same side. Two double bond on same side. Second one, reactivity increases when diene contains an electron donating group. When the diene contain an electron donating group, EDG, then reactivity increases. Okay, mainly in this position. If the electron donating group is at the first position, then reactivity is very high compared to this position. Okay, so these are the two factors affecting the reactivity of diene. Diene must be in cissoid conformation. Whenever an electron donating group is present in the diene, reactivity increases. What is the reason? In the mechanism, I already told you that the HOMO of diene will interact with the LUMO of dienophile. So HOMO of diene is actually interacting. So whenever the electron density of the HOMO increases, reactivity also increases. The electron density of HOMO increases, reactivity also increases. That means when an electron donating group is attached to the diene, reactivity is very, very high. So these are the two important factors affecting the reactivity of diene: cissoid conformation and then presence of an electron donating group. Okay, so question. Write a question. Which of the following dienes shows Diels-Alder reaction? Which of the following dienes shows Diels-Alder reaction? That is my question. First one, 1,3-butadiene, whether shows Diels-Alder reaction or not? Yes. Why? Because this diene is in cissoid conformation, so it will show Diels-Alder reaction. Okay, then next one, this diene is in transoid form. That means the two double bonds are on the opposite side, so it does not show Diels-Alder reaction at this conformation. But the system is not a rigid system because free rotation is possible. At the very next second, this double bond will rotate and it is converted. This carbon-carbon single bond will rotate and it is converted into the cissoid form. Okay, so this compound also shows Diels-Alder reaction. Why? Because this is not a rigid system. This is not a rigid system. So carbon-carbon rotation is possible. At every fraction of second, this bond is rotating. So this transoid form is converted into the cissoid form, and this will also show Diels-Alder reaction. Then my question, whether this compound show Diels-Alder reaction or not? This compound Diels-Alder reaction or not? If here two double bonds are on opposite side, and also here rotation is not possible. Why? This is a rigid system. Ring is always rigid. Rotation around this carbon-carbon single bond is not possible because this bond is a part of this ring. Rotation around this carbon-carbon bond is not possible. Why? Because this is a rigid system. rigid system. So this compound does not shows Diels-Alder reaction. Why? This is in transsoid form. This is in transsoid form. So whenever your diene is in transsoid form, you have to check that whether it is a rigid system or a non-rigid system. This is a non-rigid system, undergo rotation. So it is converted into the more reactive cissoid form prior to the reaction. But here rotation is not possible. At any condition, this compound does not shows Diels-Alder reaction. Then next question, another diene. Whether this diene shows Diels-Alder reaction or not. Whether this diene shows Diels-Alder reaction or not. Yes. Yes. Why? Yes. Why? This is in cissoid form. This is in cissoid form. Then my next question. This first diene or the second, third, fourth diene, which one is more reactive? First diene or fourth diene, which one is more reactive in Diels-Alder reaction? Okay, both the dienes are in cissoid form. Both the dienes are in cissoid form. So which diene, first one or fourth one, more reactive? The answer is, this first diene is actually a non-rigid system. First diene is a non-rigid system. Here rotation is possible. This cissoid may convert into transsoid in the very next second. This cissoid diene is converted into transsoid diene in the very next second. So there is a cis-trans isomerization is there. But this is a rigid system. This system is a rigid system. Here rotation is not at all possible. So it always exists in the cissoid form. But this is not always exist in the cissoid form. This is converted into the transsoid form. And equilibrium is present here. Cissoid is converted into transsoid. Transsoid is converted into cissoid. So due to that equilibrium, this is a non-rigid system. But this is a rigid system. Always rigid system show high reactivity. Got the point? Got the point? So our first factor which affects the reactivity of a diene is diene must be in cissoid conformation. Okay, this diene always in transsoid conformation. Reactivity not possible. Diels-Alder reaction not possible. But for this diene, rotation possible, so it can convert into more favorable cissoid form. Here this is already in cissoid form and rigid system, no rotation, so that is the most reactive diene. Most reactive diene. Then next question. What about this diene, whether it shows Diels-Alder reaction or not? Now it is in transsoid form. Transsoid form. Now it is in transsoid form. But here this is a carbon-carbon single bond. This single bond is not a part of the ring. This carbon-carbon single bond is out of the ring. So that is not a part of the ring. Okay. So here rotation is possible and this will also show Diels-Alder reaction. Why? Because this is an exocyclic single bond. Okay, exocyclic single bond. So here rotation is possible and this will also convert into the more favorable cissoid form, and that will also show Diels-Alder reaction. Okay, the next question. What about this one? Whether it is in cissoid form or transsoid form. Two double bond are on opposite side. So this is in transsoid form. Now this is in transsoid form. But don't worry, here rotation is possible. Here rotation is possible. So it can be converted into cissoid form due to the carbon-carbon rotation. So this compound also shows Diels-Alder reaction. Okay. The next one. What about this one? This is already in cissoid form. Two double bond on same side. So already in cissoid form. So it will shows Diels-Alder reaction. It will shows Diels-Alder reaction. Next one. What about this one? Two double bonds are on opposite side. Two double bonds are on opposite side. So in transferred form, free rotation is not possible. So it does not shows Diels-Alder reaction. Okay. Next one. What about this one? Two double bonds are on opposite side. Two double bonds are on opposite side and this is a ring. So in transferred form and free rotation is not possible. So this compound does not shows Diels-Alder reaction. Okay. Then this one. This double bond is already in cissoid form and will show Diels-Alder reaction. Okay. Then another example. Another diene. Here a substituent is there which is a tertiary butyl group. Here also a tertiary butyl group is there. Okay. So two tertiary butyl group at the second and third position. So a 1,3-butadiene, a substituted 1,3-butadiene. This is called tertiary butyl group. Tertiary butyl group. My question, whether this diene shows Diels-Alder reaction or not. Whether it shows Diels-Alder reaction or not. This is not a rigid system. It undergo isomerization, rotation around carbon-carbon single bond. But this compound does not shows Diels-Alder reaction. What is the reason? This compound does not shows Diels-Alder reaction because this is a bulky group. These two tertiary butyl groups are very bulky. So it undergo resonance or rotation around carbon-carbon single bond and it is converted into the trans form. Here this rotation is forward direction is most, backward is very least. Why? Because this is the most stable. Form. This is the most stable form because tertiary butyl is a bulky group. When two bulky groups are on two opposite sides, that will be more stable. So this diene always exists in transferred form. Due to the repulsion of these two bulky groups. Whenever it exists in cissoid form, heavy repulsion due to this bulky group. So it always exists in transferred form. So this diene does not shows Diels-Alder reaction because it is always exists in transferred form. That is the first point. For the reactivity of diene, the diene must be in cissoid conformation, and when the system is a rigid system, very high reactivity. Next one, compare the reactivity of following dienes. Compare the reactivity of following dienes. Okay. Compare the reactivity of following dienes. For example, here a group OCH3 is present. OCH3. Then next one, here a group CH3 is present. Here a group chlorine is present. This is simple 1,3-butadiene. Which diene is most reactive? This is A, B, C, D. Okay, A, B, C, D. Which diene is the most reactive? That is my question. Here, oxygen containing lone pair. So this is an electron donating group plus mesomeric effect. Mesomeric effect is shown by those group having lone pair of electron. Mesomeric effect is shown by those group having lone pair of electrons. So this compound shows plus mesomeric effect. Plus mesomeric effect. So it is an electron donating group and shows plus mesomeric effect. Okay, what about CH3? CH3 is also an electron donating group due to hyperconjugation effect. Hyperconjugation effect. Here hyperconjugation effect is present. But chlorine is an electron withdrawing group minus inductive effect. This is the symbol 1,3-butadiene. Okay, this effect we will discuss in general organic chemistry, GOC. Okay, so OCH3 is an electron donating group. Plus mesomeric effect. CH3 is also an electron donating group, hyperconjugation. Chlorine is an electron withdrawing group, minus I effect. This is symbol 1,3-butadiene. Okay, I already told you that whenever an electron donating group, preferably in the first position, then it will be highly reactive. This one also reactive. Whenever electron donating group is present in the diene, the reactivity of diene increases. So in the first case and the second case, there is an electron donating group OCH3 and CH3. Which one is the most reactive? Always mesomeric effect predominant than hyperconjugation. Okay, we will discuss in general organic chemistry. Mesomeric effect is predominant than hyperconjugation. So here lone pair of electron attached to a group having lone pair of electron attached to a conjugated system, then it will show mesomeric effect. So always A is the most reactive. Then second one B, because there is a electron donating group by hyperconjugation. Then B. Then comparing C and D, C is withdrawing. So definitely D. Then only C. So AB, DC is the order of the reactivity of these four dienes. Whenever an electron donating group is present, reactivity of the diene increases. This is also electron donating, this is also electron donating. Here mesomeric effect, here hyperconjugation, but this is withdrawing. Okay. Next one. Next example 2. A diene, here an OH group is present. Diene, here an NH2 group is present. A diene, here an NO2 group is present. This is symbol 1,3-butadiene. What is the order of reactivity? This is A, this is B, C and D. What is the order of reactivity? A, B, C and D. Here a group having lone pair is attached to a conjugated diene. So plus mesomeric effect. OH is an electron donating group. Here also a group having lone pair of electron is attached to carbon-carbon conjugated system. So this will also show plus mesomeric effect. Electron donating group. Here NO2 is an electron withdrawing group minus mesomeric effect. NO2 is an electron withdrawing group. See, this is symbol 1,3-butadiene. So OH is electron donating, NH2 is electron donating, but you know NO2 is a powerful electron withdrawing group. This is symbol 1,3-butadiene. My question, what is the order of reactivity? You know, whenever an electron donating group is present in the diene, reactivity will increases. Whenever an electron donating group is present in the diene, reactivity will increases. Here OH and NH2 both are electron donating. Then A or B. Compare the electronegativity of these two groups. Comparing oxygen and nitrogen. Nitrogen is less electronegative. So nitrogen will donate its electron density to the diene. Okay. Comparing oxygen and nitrogen is less electronegative. So it donates its lone pair to the diene. So definitely B is the most reactive. Then A. Then comparing C and D, then only A. This is the order of reactivity of dienes. Then another example. Example 3. Example 3. Here OCH3 is present. OCH3 is present. Which diene is more reactive? Which diene is more reactive? I already told you that whenever a diene containing an electron donating group, preferably in the first position, that will be more reactive. What is the reason for that? Here, this oxygen will donate its pi electron towards here, this will move it towards here, this will move it towards here. Extended conjugation. Extended conjugation is present. Extended conjugation is present. But here, this will move it towards here. This is cross conjugation. Cross conjugation. So in the first case, extended conjugation, but here cross conjugation. You know, due to extended conjugation, this OCH3 donates its electron density to both pi bonds. Due to extended conjugation, the OCH3 donates its electron density to both the pi bonds. But here, its electron density is donated to only one pi bond. Clear? Clear? Due to extended conjugation, this OCH3 donates its electron density to both the pi bonds, but here to only one pi bond. So definitely comparing A and B, A is more reactive than B. A is more reactive than B. So always an electron donating group in the first position will be more reactive. Okay. The next one. Example 4. Example 4. CH3, CH3. This is A, this is B. Which one will be more reactive? CH3 is also electron donating group. An electron donating group in the first position, extended conjugation. So definitely A will be more reactive than B. A will be more reactive than B. That is the question. Okay, next one, example 5. Example 5. Example 5. A conjugated diene. Here an OCH3 is present. Here a conjugated diene. A CH3 group is present. So which will be more reactive? This is also electron donating plus mesomeric effect because a group having lone pair. This is also plus donating group, but this is hyperconjugation. Donating group, but it is hyperconjugation. You know, mesomeric effect always higher, or mesomeric effect predominates than, or mesomeric effect is predominant than hyperconjugation. So which will be more reactive? Here extended conjugation is not possible, but here extended conjugation is possible. Here mesomeric effect, here hyperconjugation effect. So you have to give the priority. First priority is for effect. Second priority is for extended conjugation. Extended conjugation or cross conjugation. Extended conjugation or cross conjugation. Okay. So what about the reactivity? First priority is for effect. Second priority is for extended conjugation or cross conjugation. So definitely the effect will be higher for OCH3 due to mesomeric effect. So this is A and this is B. So definitely A is more reactive than B. A is more reactive than B. So give first priority to effect. Okay. Then next one and the last question. Example 6. This is option A. This is OCH3. Which diene is more reactive, whether A or B? A or B? Which one is more reactive? A or B? Here this is a rigid system and in cissoid conformation. But this is a non-rigid system. This ring is rigid because rotation is not possible. Always exists in cissoid form. But this is non-rigid. It will undergo rotation and convert into the less reactive transsoid form. So definitely A is more reactive than B. A is more reactive than B. So that is about the reactivity of diene. Whenever an electron donating group is present in the diene, it will be more reactive. Give more importance to mesomeric effect. That means group having lone pair. Then hyperconjugation. Okay. Withdrawing group decreases the reactivity. Then an electron donating group in the first position will be more reactive than second position due to extended conjugation. Then what about the cissoid and the transsoid conformation? A diene in cissoid conformation and a rigid system, it will be more reactive. Okay, next one, reactivity of dienophiles. Reactivity of dienophiles. Okay. So please listen. Whenever an electron withdrawing group is present in the dienophile, it will be more reactive. Why? Because you know, whenever we studied the mechanism, I already told you that whenever an electron withdrawing group is present in the dienophile, because the LUMO of dienophile is actually reacting. For diene, HOMO is reacting. For dienophile, LUMO is reacting. LUMO is the lowest unoccupied molecular orbital. So when an electron withdrawing group is present in the dienophile, reactivity increases because for dienophile, LUMO is reacting. Okay. So what are the common electron withdrawing group? NO2 is a powerful electron withdrawing group. CHO is electron withdrawing group. COOR is electron withdrawing group. Chlorine, halogens are electron withdrawing group, etc. Okay. So when such electron withdrawing groups are present in the dienophile, it will be more reactive. So I write an example or write a question. Here a dienophile, double bond COH. This is A. The next one, double bond NO2. This is B. The next one, double bond CH3. Then fourth one, double bond Cl. This is C and this is D. What is the order of reactivity? Okay. C double bond OH is an electron withdrawing group minus mesomeric effect. NO2 is also electron withdrawing minus mesomeric effect. CH3 is electron donating plus hyperconjugation. Chlorine is electron withdrawing but minus inductive effect. Okay, mesomeric effect is more predominant than inductive effect. Mesomeric effect is the most predominant. Okay, mesomeric effect more predominant than inductive. So in option A, B and D, both are electron withdrawing, but A and B is mesomeric, D is inductive. So what is the order of reactivity? Okay, here comparing C double bond O and NO2. NO2 is the most withdrawing. We will discuss a series of electron withdrawing group in the general organic chemistry section. NO2 is the most withdrawing. So option B is most reactive. Then option A. Then option D. Then option C. Why option C? Because option C is electron donating group. So whenever an electron withdrawing group is present in the dienophile, that will be more reactive. Okay, so comparing these four options, option B is the most reactive because NO2 is powerfully withdrawing. Then C double bond OH. Then chlorine because chlorine is inductive effect. Then only CH3 because CH3 is an electron donating group. Okay. Then write a question. Please write a question. Which is the most reactive reaction or which is the most fast reaction or reactive reaction? Option A, a diene, 1,3-butadiene plus a dienophile containing NO2. This is the first reaction. Then B, a diene option B, here a diene is present and this diene containing a CH3 group plus a dienophile containing an electron withdrawing group CHO. Then option C, a diene which containing an electron donating group OMe plus an electron withdrawing group NO2. This is option C. Then option D, a diene containing an withdrawing group OMe plus CHO. So which is the most reactive? Here this is simply a 1,3-butadiene. Here electrophile containing withdrawing group. Here diene containing electron donating group and dienophile containing electron withdrawing group. Here also diene containing electron donating group and dienophile containing electron withdrawing group. Here diene containing electron donating group, dienophile containing electron withdrawing group. Whenever you compare the effect, here plus mesomeric effect, most donating, NO2 is the most withdrawing, minus some. So definitely option C having the most, option C, that reaction is the most reactive reaction or the most fast reaction, because OMe having higher donating effect, NO2 having higher withdrawing effect. In general, we can summarize, if your diene having an electron donating group preferably in the first position plus your dienophile having an electron withdrawing group, then that reaction will be very fast reaction. What is the reaction? 1 cycloaddition, 2 plus 2 cycloaddition, and you will get a product. The regioselectivity of the product that we will discuss later. Okay, so this is the reaction. So that's about some typical systems of diene, typical systems of dienophile, reactivity of diene and reactivity of dienophile. Okay, then some examples of Diels-Alder reaction. Some examples of Diels-Alder reaction. Okay, moving to the first example. A simple diene, 1,3-butadiene plus a dienophile. What is the reaction? This pi bond make a sigma bond here. This will move towards this here. Okay, giving number, this is 1, 2, 3, 4, 5, 6. So a 6-membered cyclic ring is formed. So you can give a number, this is 1, 2, 3, 4, 5, 6. Between 2 and 3 a pi bond is formed. Between 1 and 6 a new sigma bond is formed. Between 4 and 5 a new sigma bond is formed. Okay, then example 2. A substituted diene plus malic anhydride. This is malic anhydride. What is the product? Okay, electron shifting, this will make a sigma bond here, this move towards here a new sigma bond is formed. So 1, 2, 3, 4, 5, 6. A 6-membered ring is your product. A 6-membered ring, between this carbon a pi bond. Here a substituent CH3 is present. Remaining portion of the dienophile, double bond O, O, that is the product. Okay, that is the product. Question number 3. Third question. Third example. Example 3. A cyclic diene plus a dienophile C double bond OH under thermal condition. All these reaction taking place under thermal condition. You know 4+2 reaction takes place under thermal condition. What is the product? Here a diene is present. 1, 2, 3, 4. This is a diene. This is 5, 6. So reaction, this pi bond attack here, this will move it towards here, this will make a new sigma bond here. So 1, 2, 3, 4, 5, 6. A 6-membered ring is your product. Giving number, this is 1, this is 2, this is 3, 4, 5, 6. Between 2 and 3, a pi bond is formed. At the carbon number 6, a C double bond OH is present. Okay. Between 1 and 4, another carbon is present. A bridged carbon is present. Between 1 and 4, a bridged carbon is present. This is carbon number 1. This is carbon number 4. Between 1 and 4, a bridged carbon. But in your CSIR exam question paper, this product is given in another form equivalent to. The 6-membered ring is represented like this. Okay, 1, 2, 3, 4, 5, 6. Giving number, this is 1, this is 2, this is 3, 4, 5, 6. You know between 2 and 3 there is a pi bond. Between 1 and 4 a bridged carbon is present. Between 1 and 4 a bridged carbon. This is the bridged carbon. At the carbon number 6 there is a C double bond OH. This is the product. So the same product is represented in your question paper in this fashion. Okay, that is example 3. Okay, then example 4. Example 4. A diene, a cyclic diene plus a dienophile C double bond OH. What is the product? Diene and a dienophile. How you can write the product? Ring formation. Giving number, this is 1, 2, 3, 4, 5, 6. So a 6-membered ring is your product and these two carbon act as a bridge. Okay, a 6-membered ring is your product. A 6-membered ring can be represented like this. A 6-membered ring, this is 1, 2, 3, 4, 5, 6. Okay, so between 2 and 3 a pi bond is present. Between 2 and 3 a pi bond is present. At the carbon number 6 there is a C double bond OH. Okay, then between 1 and 4 a bridge is there and this bridge containing 2 carbon. Between 1 and 6 a bridge is present and this bridge containing 2 carbon. So this is the bridge and that bridge containing 2 carbon. That is the product. Okay, so carbon number 1 and carbon number 4 they contain bridge and this bridge contain 2 carbon. So that's the product. Clear? Okay, then question number 5. Question number 5. This is a special diene plus a dienophile C double bond OH under thermal condition. This reaction is also thermal condition. All 4+2 reaction takes place under thermal condition. What's the reaction? This is the 2 double bond that you have to consider. So this pi electron attack here, this will move to here, this will make a sigma bond here. So 1, 2, 3, 4, 5, 6. A 6-membered ring is your product. 6-membered ring can be represented like this. This is 1, 2, 3, 4, 5, 6. Okay, between here also numbering 1, 2, 3, 4, 5, 6. Between 2 and 3, a pi bond is present. Okay. At carbon number 6, a C double bond to OH is present. C double bond to OH. Between 1 and 4, a N double bond N bridge is present. Between 1 and 4, a N double bond N double bond N bridge is present. So that's the product. Okay, N double bond N bridge. Clear? Okay, example 6. Example 6. A special diene plus dienophile is alkyne. Alkyne also act as a typical dienophile. Alkyne. So giving this pi bond of alkyne attack here, this will move towards here, this will make a sigma bond here. So giving number, this is carbon number 1, 2, 3, 4, 5, 6. So a 6-membered ring is your product. A 6-membered ring is your product. Okay, giving number, this is 1, 2, 3, 4, 5, 6. Between 2 and 3, there is a pi bond. Between 6 and 5, one pi bond is remaining. One pi bond is remaining. Between 1 and 4, a OC double bond of bridge is present. Between 1 and 4, this carbon number 4 is connected to C double bond O. 4 is connected to C double bond O. Then an oxygen, this oxygen is connected to carbon number 1. So that is your product. Clear? This carbon number 4 is connected to a C double bond O, then that O is connected to carbon number 1. So that's your product after cycloaddition reaction. This reaction also takes place under thermal condition. Then seventh example. Another special diene. This will also act as a diene. C double bond O plus. Here our dienophile is benzene. Reaction taking place under thermal condition. Benzene is your dienophile. So benzene, the triple bond on benzene attack here. This will move it towards here. This will make a sigma bond here. So giving number 1, 2, 3, 4, 5, 6. So a 6-membered ring is formed. A 6-membered ring is formed. That 6-membered ring can be represented in this fashion. Giving number, this is 1, this is 2, this is 4, 3, 4, 5, 6. Between 2 and 3, a pi bond is formed. Okay. Between 6 and 5, one pi bond is also remaining, and here a benzene ring is also remaining. Then at 1 and 4, a bridged C double bond O is present. At 1 and 4, a bridged C double bond O is present. So that's your product. So cycloaddition reaction, simply what type of reaction all these? All these are 4+2 cycloaddition reaction or your Diels-Alder reaction. A 4+2 cycloaddition reaction or a Diels-Alder reaction. Okay, next question. Question number 8. Question number 8. This is also a special diene. Here these two double bonds that you have to consider. A dienophile, alkyne. Alkyne act as a dienophile. Condition thermal. What type of reaction? This pi bond attack here, this will move it towards here, this will make a new sigma bond here. This is carbon number 1, 2, 3, 4, 5, 6. So a 4+2 cycloaddition reaction. After that a 6-membered ring is formed. A 6-membered ring that you can represent in this fashion. Okay, this is carbon number 1, carbon number 2, 3, 4, 5, 6. So between 2 and 3 a new pi bond is formed. Between 2 and 3 a new pi bond is formed. Between 5 and 6 already one pi bond of the alkyne is remaining. When between 1 and 4 a bridge is present. Between 1 and 4 a bridge. That bridge is S double bond O. S double bond O. Double bond O. That is the bridge. Clear? The question number 9. Question number 9. This is furan. Furan is least aromatic, so it will undergo Diels-Alder reaction. On reaction with the malic anhydride, double bond O, under thermal condition. This is a 4+2 cycloaddition reaction. How you can represent that 4+2 cycloaddition reaction? This is the 4+2 cycloaddition reaction. A 6-membered ring is your product. A 6-membered ring. 1, 2, 3, 4, 5, 6. So a 6-membered ring is your product. That can be represented like this. This is 1, 2, 3, 4 and 5 and 6. Okay. So between 2 and 3 a new pi bond is formed. Between 2 and 3 a new pi bond is formed. Between 6 and 5 the remaining portion of the malic anhydride. This is the remaining portion of malic anhydride. Between 6 and 5. Okay. Then between 1 and 4 an oxygen bridge is present. Between 1 and 4 an oxygen bridge is present. Carbon number 1 and 4. So that's your product. That's your product. Clear? Okay, then question number 10. Question number 10. Anthracene. This is anthracene. Okay. On reaction with a dienophile NO2 under thermal condition, a typical example of 4+2 cycloaddition reaction. You know this middle ring of anthracene will act as the diene. This middle ring. So this pi bond attack here. This will move it towards here. This will make a sigma bond here. So you can draw the anthracene as such. 3 6-membered rings. Okay. Here a pi bond is there. Here a pi bond is there. What happens to the second ring? Second ring giving number 1, 2, 3, 4. This is 5. This is 6. Between 2 and 3 a new pi bond is formed. This is 1, 2, 3, 4. Between 2 and 3 a new pi bond is formed. Between 1 and 4 a bridge is present. That is 5, 6. Between 1 and 4 a bridge is present. Between 1 and 4 a bridge is present, and that containing 1 is connected to this is 4 is connected to 5. 4 is connected to 5, 1 is connected to 6, and at 6 there is an NO2 is present. At 6 there is an NO2 is present. This can be represented in another fashion. The middle 6-membered ring. The middle 6-membered ring. 1, 2, 3, 4, 5, 6. Between 1 and 4 a bridge. That bridge containing 2 carbon, and here an NO2 is present. Okay. Then here a 6-membered benzene ring. Here also a 6-membered benzene ring. That's your product. Okay. You can here a pi bond is present. So in this fashion also you can represent the product. Okay. Then question number 11. Question number 11. A diene plus a dienophile under thermal condition. This is a diene. That's a dienophile. Here two dienophiles are there. This is dienophile A, this is dienophile B. My question here, selectivity is there. Which dienophile will react? Which dienophile will react? Dienophile A or dienophile B? In dienophile B, there is an electron withdrawing group. Whenever an electron withdrawing group is present in the dienophile, that will be more reactive. When an electron withdrawing group is present in the dienophile, that will be more reactive. So definitely the dienophile B will be more reactive. So you can write the product. This dienophile make a bond here, this will move towards here, this will make a sigma bond. So carbon number 1, 2, 3, 4, this is 5 and 6. This is 5 and 6. So a six-membered ring is formed. A six-membered ring. This is 1, 2, 3, 4, 5, 6. Between 2 and 3, a new pi bond is formed. 1 is connected to 6 and this 6 contain an NO2. 4 is connected to 5 and remaining portion of the ring is another aromatic ring, benzene ring. Not aromatic ring. This is the product. Clear? This is the product. Okay. You can write the reaction by reversing the diene, because this portion of the diene is reactive, because that diene containing an NO2, an electron withdrawing ring. Okay. Then 12th question. A 1,3-buta diene plus quinone. This is quinone. Here an NO2 group is also present. Under thermal condition, definitely this is a 4+2 cycloaddition reaction. Here this is diene. Two dienophiles are present. Dienophile A, dienophile B. Which is more reactive? Definitely dienophile A is more reactive because it is containing an electron withdrawing group. So this will attack here, this will move towards here. Here a new sigma bond is formed. So a six-membered ring is your product. A six-membered ring giving number, this is carbon number 1, 2, 3, 4, 5, 6, between 2 and 3. 1, 2, 3, 4, 5, 6, between 2 and 3 a pi bond is formed. 1 and 4 is connected to the quinone ring. Okay. And at the carbon number 6 an NO2 group is present. So that's your product. And last question number 13. A diene plus quinone, double bond O. Here a CH3 group is present and here an NO2 group is present. Reaction is under thermal condition. What is the product? Here two dienophiles are there, dienophile A and dienophile B. You have to select first one containing a withdrawing group, second one containing a donating group. You know, dienophile must contain electron withdrawing group. So dienophile A is most reactive. So this will attack here, this will move towards here. A six-membered ring is formed. A six-membered ring. You can give a number. This is 1, 2, 3, 4, 5, 6. Between 2 and 3 a pi bond is formed. Between 6 and 5 the remaining portion of quinone is there. This is 1, 2, 3, 4, 5, 6. Okay, at carbon number 6 an NO2 is present. Here a CH3 is also present. So that's the product. Okay, so these are some simple examples of Diels-Alder reaction.